So this integrand has a sech x, which means it's going to have, that's 1 over cos x, and we know that, 1 over cosh x. We know that cosh x has zeros along the imaginary axis, infinitely many zeros along the imaginary axis. So this is going to have infinitely many poles above the real axis. So we can't use a semicircular contour, we have to use a rectangular one. So our rectangular contour would be going from R to minus R. The key question is, what height of contour do we need? Okay, so let's just write this another way to start with. We'll write it as cosh of x. Incidentally, this condition on A is important. As soon as we see an exponential, we should be worried if the integral is from minus infinity to infinity, because obviously this part here goes to infinity, either of those limits. But because sech x, because A is less than 1, modulus of A is less than 1, this on the bottom, which is of course half e to the x plus e to the minus x, will beat this thing on the top. So the integrand itself will indeed go to 0 as x goes to plus or minus infinity in all cases. Okay, so remind ourselves that cosh of I, cosh is like cos, but it's rotated 90 degrees. So instead of, we know that cos of x has zeros at n plus a half pi. So we have simple poles at z equals n plus a half pi I in this case. What other things do we know? Well, we have to think what happens if we, I mean, in this case it's going to be possibly something we're going to have to do by trial and error. To make life easier for ourselves, the other thing to say is that we should try and make this W as small as possible, this height as small as possible. If we make it too big, then we have more poles inside the rectangle in order to evaluate residues of. So it's the sum of the residues. We want as few as residues as possible to have to evaluate. So if we've only got one, that's ideal. So we need to choose the minimum possible value of W. So we just have to look at this function and say, well, what do I know about cosh? Well, you might remember that cosh plus I pi is simply equal to minus cosh of x. So cosh of x plus I pi is equal to minus cosh x. If I change that to pi by 2, I don't get anything. There's nothing I would recognize. So this would be, pi would be a reasonable guess for a reasonable thing to try for the width of this contour. So let's, it would also seem to make sense because that way we'll get just one pole inside, because obviously when n equals 0 I get half pi I. So the pole would be here. The next one would be when n equals 1 I get 3 halves pi, so that would be up here. So choosing this height to be pi would seem like a sensible choice. So we'll try that and see what happens. So we consider the limit as r goes to infinity of e to the az and cosh z on the bottom around gamma. So as r goes to infinity, this along here is the integral we want. then we should, if we're being thorough, we should consider this integral here and show that it goes to 0. So what do we have here? Well, along here we've got z equals r plus iy. Here we have z equals minus r plus iy. So we've got y is being integrating from 0 up to pi, and we're taking the limit as r goes to infinity. And we have e to the a, and what's z? So z is r plus iy, and dz is just I times dy, and we're dividing by cosh of z. So cosh of z, well, it's cosh of r plus iy. Well, we sort of remember that cosh is, of course, e to the something plus e to the minus something. We're not really worried about what the iy does. We're worried about what the r does. So basically we've got e to the r on the bottom, and we've got e to the ar on the top. And as the r goes to infinity, this overall will always tend to r to the a minus 1. Sorry, tend to e to the a minus 1 r. So we're safe as long as a is less than 1. This will tend to 0. Okay. Now, integrating back along here, what happens? This is the crucial bit. What we want, what we're hoping for, is that this integral along here will be a multiple of I. Then we should be able to, which is not just minus I. So integrating back along here, z is equal to x plus I pi. So, okay, x going from infinity to minus infinity. Sorry, plus infinity to minus infinity. And we have e to the a x. Now, z now is plus a I pi, so it's x plus I pi. So we've got an extra I a pi coming along from this. We substitute in here. It's dx, and cosh of x plus I pi, we've already said, is just equal to minus cosh. So we end up with cosh x on the bottom, and we change this to a minus sign. So this is looking hopeful, because this is just a constant, which we can take outside, and then this thing here is precisely minus I. Okay, so it looks like we'll be fine. Then the last integral we do is this, which it works out in a similar way. We'll just do it quickly, just to check. So it's r, limit as r goes to infinity of, so integrating from y equals pi to 0, and it's e to the a times minus r plus iy, I dy over cosh of minus r plus iy. So again, by this similar sort of argument, this will be of order e to the a times well, okay, in this case, it depends. Well, okay, the important thing is it depends on what a is. If a is positive, then we don't have a problem anyway. If a is negative, then this will be positive overall. So okay, well, okay, it's not going to be a problem anyway. But whatever happens, this is going to tend to 0. But okay, well, I'll write it out anyway. So we've got a to the minus r, and this is going to have e to the r on the bottom, so that's going to be minus r. So anyway, whatever happens, whether this is positive or negative, this will tend to 0. So we just get left with this and this. So this thing then is equal to 1. So I'll swap the limits and change it into a plus sign, and I've got e to the ia pi times the integral I want. So that's going to be equal to 2 pi I times the residue of the pole we have here. So this is 2 pi I times the residue of e to the az over cos z at just pi by 2 I. So again, this is P over Q. So this gives us P is e to the A, and then I've got pi by 2, pi I by 2, write it like that. And I differentiate this and substitute in, so I've got sine of pi by 2i. So sine of pi by 2i is the same as I sine of pi by 2. So this is simply I. So we end up with I equaling, so this cancels with this, and I've got 2 pi e to the I pi by 2 divided by this thing. So this is when simplification tricks become important. Obviously I need to get a real answer, since this is a real integrand. Multiplying top and bottom by e to the minus this thing here will give me something nice. So multiplying by minus this, and I recognize this as this thing here, of course, is cos of a pi by 2. So I then just get the answer pi over cos a pi by 2.